Brett.
Nice meeting you, Brett.
Come on in.
Thank you.
So how you been since we saw you a week ago?
Pretty good, pretty good. Just
Doing good?
working on my project and everything.
Do anything fun this weekend or anything?
My girlfriend and her sorority for
Okay, that's cool.
winery and passing. It's fun.
Why
How
not
about you?
pass? So very nice. Yeah, I didn't do anything too crazy.
No.
Watched some dope movies. Saw Gladiator for the first time. It was cool. I finally got around to it.
Yeah, nice.
Bought some Legos,
Sweet.
Star Wars.
Sweet.
It was a pretty fun weekend for me. But so yeah. Well, let's get into it here. I made an agenda.
Cool.
First things first, want to clarify the ending time.
Okay.
Want to know if you still have 20 minutes to meet today.
Yeah.
Awesome. So it's going to put us about what? 5:04 here. I'll write that down on the agenda here, just so we know when to end it. I also want to discuss what to talk about. Due to the issue of our time, I think it's a good conversation that we figure out what's most important
Cool.
because we need to recognize we might not get to everything.
Mm-hmm.
So I wrote down 3 topics here. The method that we use to impute the missing values for our data.
Mhm.
And we ran 2 analysis models. I believe the second one's more interesting, but I was just wondering if you had a preference on, what would be most important for you to hear about.
I guess I'm most interested in like the results.
The analysis? Okay, cool.
Yeah.
That's what I like to hear. Just mark down some notes here. All right, so first things first, before we get into results, I want to have a conversation and develop a better understanding for the background
Okay.
of your project. I wasn't here at the table in your initial meeting, but I was listening, and I noticed that you and your friend talked about already doing some basic stats on the data.
Right.
And I was just curious, was that actually, were you doing the basic stats? Do you know about the basic stats already performed? I just wanted to know a little more about that.
What kind of basic stats you use?
Well, you said that we did some basic stats, so I was just wondering what you did. You know?
Well, we just started off originally with like linear regressions, and then I went and met with Dr. Walker, the stats department. He like gave us some new ideas. We were trying some of that. I was one of the bio professors. He was steering me to art, which is where I ended up.
Okay.
And then we were doing things like principal component analysis, which I don't really understand.
Principal component analysis. Yeah, it's a little complicated.
But was doing that anyways. So I mean,
Sure.
just kind of, I haven't like done too deep.
Okay. When you were doing the linear regression, do you remember what response variable you were testing? Were you testing just one of them, or all 4 of the boldness
We were
variables?
testing them all
Trying all 4 of them? Okay. Interesting. I just want to know, just to develop a better understanding for what we're working with here. Great. So when we first got the data,
Yeah.
our group had a good conversation about, what defines the boldness of a fish, right? Is it, the number of approaches, or is it the proximity or the latency to leap?
Mm-hmm.
And we had some interesting conversations, right off the bat. Let's take the number of approaches, for example. Right off the bat, I was thinking, a fish with more approaches must be a bold fish, right?
Yeah.
A fish who approaches the predator 11 times. That's pretty bold, right? But then I was thinking about it more, and I was looking at the data set,
Mm-hmm.
and I would see things that don't make sense in it. For example, take for the fact a fish who approaches the predator and hangs out the rest of the trial right next to the predator.
Right.
That's pretty bold, in my opinion.
Pretty bold.
Mm-hmm. But in the data set, he's only going to have 1 approach.
Mm-hmm.
Now think about I think there was a fish in the data set with 11 approaches.
Yeah.
That seems pretty bold as well, but if you're approaching 11 times, you're also swimming away 11 times. So I don't know what the proximity value for that fish with 11 approaches, but technically he could still have like a proximity of 4 or 5 and have 11. You know what I mean?
Right.
Like it's still there's like a similar paradox with exploration.
Mm-hmm.
You think, okay, well, fish swimming around more, more likely to be next to the predator, probably more bold if a fish has a high exploration value. But there's that similar, paradox with what about the fishes that swim up right to the right next to the predator. Don't really move around, but just spend a good majority of time chilling in those danger zones, you know? So we found, you know, they don't really tell the whole story with explaining boldness.
Right.
Would you agree with that?
Yeah, I'd agree. I mean, you're going to be collecting partial data and then biological experiments.
Yeah.
It's like we can interview the fish and say, how bold are you? So we have to pick at these characteristics that we can define and then use whatever method.
Yeah, it's not like you can like,
exactly.
like, okay, this fish is bold, you know, like, but.
Right, boldness is a pretty abstract term.
Cool.
So.
I just want to share, you know, some of the things we were thinking about. Same thing with latency to leave.
Mm-hmm.
You think, you know, hey, maybe a fish who leaves the safe zone sooner, that's going to be a more bold fish.
Mm-hmm.
But, you know, then you get examples of, you know, fish who leave the safe zone immediately, but spend the whole time hanging out in, you know, zone 3 or 4.
Yeah.
And then a fish who might leave the safety zone 70 seconds in, but swims right up to the predator and, you know, is like in the danger zone for the majority of the time. And then we started thinking about proximity. And we couldn't really find any, you know, paradoxes, I guess you could say, with proximity. We figured a fish who is bold is always going to have a higher proximity value than a less bold fish.
Right.
So out of the 4 response variables that we were given, we decided that proximity does the best job of explaining, or the best, most consistent job of explaining boldness. And if it doesn't have any, it tells the whole story more accurately than the all 4 response variables. And then what we did on top of that, we were thinking, okay, well, proximity does a great job. What if we could come up with a new variable that does an even better job of explaining boldness? So what we did, we created a new variable and we called it boldness. It's a categorical variable which has 2 possible outcomes, yes or no. The fish is either bold or it's not bold.
Yeah.
To be categorized, let's draw my pencil. To be categorized as a bold fish, the fish had to have a proximity value of at least 5 and had to have at least 1 approach in its 300-second trial.
Right.
And we were just thinking about it, you know, it made sense. It made sense to us. Like, that'd be a pretty good way to classify whether or not a fish is bold, compared, you know, just compared to the rest of the fish in the study. So let's open up our memo here. And let's get into it. I'm going to flip to the page and tell you the page number here. All right, it's on page 10. So this is what's called a logistic regression model. It's basically, what do we need to predict? We need to predict our new boldness variable, which is a categorical variable. So this is different than linear regression, where you're predicting a quantitative continuous variable.
Right.
So we have 2 possible outcomes. And how logistic regression works is, you know, thinking in simple terms, you think, well, what if we could, you know, predict the probability that the fish is bold or not, like a number between 0 and 1.
Right.
That kind of makes sense. But how logistic regression works is it works slightly differently. It predicts what's called the log odds. Now, odds is a little different than probability. It's if you have a 50% chance of success, that's the equivalent of saying my odds are 1 to 1. For every 1 success, I'll have 1 failure. So the formula for odds looks like, I believe it's probability divided by 1 plus the probability, something like that. Now in this model, it's actually computing the log odds. So it's taking the log of the probability divided by 1 minus the probability. It's a little confusing, but I'll try and explain it as best I can when it comes to interpreting these coefficient values in our model.
Okay.
So right down here, we see the 2 predictor variables we used, mass and gonopodium black area. I'm just going to flip to a new page here just to show you what that regression logistic regression. You can stay right there if you want. This is what the logistic regression model looks like. You're familiar with linear regression, so I'm sure something like this equation looks a little more familiar. Pretty much the same thing going on here. That beta 0 is our intercept value, and we can think of x1 as the male mass and x2 as the gonopodium black area.
Why did you choose those 2?
I was hoping you'd ask. So when we when we selected our response variable, our boldness variable, we used what's called a stepwise selection method, where basically we have no parameters already inserted in the model, but we can see which parameters would have the most significant effect right off the bat, kind of, with our response. And male mass did the best job, had the most significant, the lowest p-value, if you will. It did the best job explaining the most variability within the logistic odds for a fish being bold or not.
Right.
Once we had mass inserted, the effect of that gonopodium black area was very interesting, which is why I wanted to include it. I hope you find it interesting as well. My first thoughts for it were issues of multicollinearity. Multicollinearity is when two of your predictors are heavily correlated with each other. Now, these morphology variables, they're all heavily correlated with each other. Fortunately, it worked out that gonopodium black area and male mass were like one of the two morphology variables that were not very correlated with each other as compared to the others. And it tends out to work well in this model. The issue with multicollinearity is when you do have two predictors that are heavily correlated with each other, it often will not tell the whole story of the effect of each individual parameter, the effect of those parameters that has on the predicted response, if that makes any sense at all. But so say, for instance, if these two were heavily correlated, we can't really trust these estimated coefficient values for what they are. But that's not the case, so we don't have to worry about that. So what was I going to say here? Okay, so I'm going to start just helping you interpret the coefficients here.
Yeah, cool.
And then I'll get into more about that gonopodium black area and explain why it's so interesting.
Okay.
Let me just read the coefficient value. So coefficient value for mass is negative 29.2777. That's equivalent to our beta 1 here. Now, let's see, I'm going to get some. This is my memo, so I can write on it here. I'm sure you're familiar with math, but we're just going to call this term here odds. So I'm just going to write odds is equal to e to the power of all this right here, right? And we can separate that out to e beta naught times e to beta 1 times x1 times e to beta 2 x2. This is basically the equation. Now, so we have, this is our beta 1, this is our coefficient for mass right here. So, negative 29.2777. What this means is, for every 1 unit increase in male mass, for every 1 gram increase in male unit mass, this S to this B1 coefficient is going to change by, it's going to go down negative, or 29.277. So what this does is, for every 1 unit increase in male mass, the log odds, or not the log odds, excuse me, the odds of a fish being bold decrease by a factor of e to the negative 29.277.
Yeah.
For that, now it's weird, right? So that's every gram increase. That's not really relevant for the sake of this data, because the grams are, you know what I mean? There's no fish that's like has a whole gram mass bigger than the other fish. They're all like, I think the biggest difference is like 0.2 or something. And you know what I mean? So you can simplify it down. You can divide everything by 10, and you can say for every 0.1 gram increase in male mass, the odds of a fish being bold decrease by a factor of negative 2.927. So you divide this number by 10 as well. And what that means, what do I mean by decrease by a factor of? So that means we'll take the odds before that we have, multiply it by e to the negative 2.2777. E to the negative 2.77 is going to be what? It's going to be a fraction. It's going to be less than 1. So we'll take the odds before, and we're going to divide it by something, which is going to lower the odds. So that's the reason for this number being negative. So as grams increase, the odds of being bold decrease.
Right.
So larger fish with more mass, are less likely to be bold. that's how you interpret the model now.
Yeah, cool.
In terms of the confidence interval over here, are you familiar with have you heard the word confidence interval
Yeah.
before? I thought you had. So we can think about this as kind of so this is just the model that we formed from the data that we collected from our sample.
Mhm.
Now, our goal is to be able to generalize these results to the entire population of fish, like the ones that you use in your study.
Right.
So we are 95% confident that true effect of male mass lies somewhere between
Mhm.
these two numbers.
Which are both negative. So.
Which are both negative, exactly.
Hmm.
Which results in that significant p-value. So I see you have some understanding of how that works already.
Yeah. Yeah, that's cool. That's neat result.
Um,
How does the gonopodium black area?
Yeah, let's talk about gonopodium black area. So what that means is the reason we included this in our model,
Mhm.
you can see it's not significant.
Right.
However, it is fairly close,
It's close, yeah.
a little bit. It's larger than 0.05. The reason we included it is it increased our R-square value for our model.
Mhm.
R-squared is a measurement of the variability in the data that is explained by the model.
Yeah.
So you want a higher R-squared value. It's a more accurate model.
Mhm.
It also lowered these values, AICC and VIC.
Mhm.
I cannot really explain to you how those values are calculated, but you want those to
I've
be
read up
lower.
a little bit on those, yeah.
Yeah, I don't really understand those too well, to be
Mhm.
honest, but you want those to be as low as possible.
Okay.
So adding this to our model also lowered those two values.
Yeah. Hmm.
So what does this gonopodium mean? What does this coefficient mean? So because gonopodium and male mass is in there, this effect of gonopodium black area is taken into account after already adjusting for mass. So what this means is fish with similar masses tend to be more bold if their gonopodium black area is larger.
Mhm.
This is very confusing,
No,
which is
that
why
makes
we put out a graph here. So you can think of the red intervals as fish who are bold, and the blue intervals who fish are not bold.
Okay.
According to those conditions we said, proximity,
Yeah.
at least 5, at least 1 approach.
Mhm.
Now we're looking at mass intervals. So within each one of these vertical bars, if you will, there are fish with similar mass
Mhm.
in our study. And the y-axis is the gonopodium black area. So you can see that there's one little area here where there appears to be no association with the gonopodium black area,
Right.
but for all the others, the boldness likelihood, I guess you could say, is greater for fish with greater gonopodium black areas. This is already after accounting for mass.
Right.
When you look at
Factoring out
gonopodium
mass.
black area just on its own,
Mhm.
it's not significant at all. But I just found this very interesting,
Yeah, that's cool.
and it's not quite significant, but it's definitely, it could be proven significant if we up the sample size of our study.
Yeah, it's super close.
I actually went into it a little bit further on the next page, and you can read about that in your own free time.
Mhm.
But right now, it looks like our meeting is coming to a close, so I just want to take a second to, conclude, just summarize everything we went over. I just brought you through one basic model that we did. We talked about how my group interpreted the individual boldness response variables that you gave us. How well did they do at explaining the boldness of the fish?
Mhm.
Did they really tell the whole story, if you will? We decided proximity did the best job out of those 4, and we eventually came up with a new variable that we thought did an even better job. And we fit a logistic regression equation on it. Mass proved to be heavily significant.
Mhm.
Interesting effect with the gonopodium black area, which I hope you find interesting
Yeah,
as well.
that's pretty cool.
Was there anything else you want? We have like a couple minutes left. Is there anything you're kind of not too sure about that you want to talk about?
So you did all your analyses and jump, looks like?
The only analysis and jump, we included a do-it-yourself R section in
Okay.
the very back of the memo. So every graph and model we produced is right in the back. We titled what it is right above the code,
Right.
so you could run it yourself. That's what you wanted, yes?
Yeah, that's cool.
Excellent.
Awesome. Yeah, it looks great. It's really interesting. I like the
piece part of the variables. It's pretty cool.
Yeah, we were thinking about that. It's interesting. Are you turning this in before you are you graduating?
I'm graduating in June, but I probably won't be done with this project.
Yeah, it's a complicated project.
Yeah, still writing, so waiting on these actually. See what I can use from it.
Awesome. Yeah, I hope you find it interesting. And,
Yeah, really cool.
Get some use out of it.
Definitely.
All right.
If
So
you have
you
any
good?
questions, yeah.
Awesome. I'll walk you out here.
Yeah.